Okay, today we're talking about limits of trig functions. Okay, and we're going to get to this in a minute, but this is the special trig limits that we're going to try and get our problem to look like, right? We're going to want it to look like this eventually, and the special trig limit is that the sine is 1, the sine of c theta over c theta. If your numbers, right, are the same, then the limit of that function is 1. And over here, if we're talking about 1 over the cosine, 1 minus cosine theta over theta, that limit is 0. Okay, these are special trig limits that we're going to be trying to make when we're simplifying these problems down here. But let's start first things first. Okay, so once again, direct substitution is the way to go if we can do it. Okay, just plugging in directly your x value into your thetas and simplifying to see if you get something good. Okay, the only time it doesn't work is if your denominator is 0, right? And then we have to do some other things in order to rationalize or somehow make our denominator no longer 0. Okay, so direct substitution works first, so that's what you should always try first, is direct substitution. So with our first example, when we plug it in, we do all of our nice math and we come out with an answer of 0. So the limit of this function as x or theta approaches 2 pi over 3, the y value is going to be 0. Okay, so same thing with our friend over here. Let's do direct substitution and see what our y value is. So for our second example, the y value is 2. As your theta approaches pi, the y goes to 2 for our 2 cosine squared theta function. Okay, direct substitution is great and easy when it works. Okay, when it doesn't work, that's when we have to do something else. Like in this case, 1 minus cosine over sine squared. Right, when we plug 0 into sine squared, the sine of 0 is 0 and 0 squared is 0, so now we've got problems. Right, we have to do something else. And what we're going to do is remember our trig identities. Ooh, trig identities. And we're going to replace sine squared with its trig identity. Okay, so we're going to do some manipulation with substitution so that we can use direct substitution in a minute. Okay, so let's do that right here. And this is what our substitution would look like. Okay, replacing sine squared with its trig identity, factoring that 1 minus cos squared, and canceling so that you finally have a trig function that you can use direct substitution with. Okay, the point is to make something that can use direct substitution with. So let's do some practice of these three that are all going to be able to use some trig identities in order to simplify before you start to use direct substitution. And these are your answers when you do your trig substitution. Okay, things cancel out nicely and you're able to use direct substitution to get a direct answer. Okay, so we try to do either trig identities or direct substitution, but when that doesn't work, we're going to use these two special factorizations. Okay, the secant of some number, right, times theta over that same. These things are the exact same. That equals 1. Okay, or if we can make 1 minus cosine over theta, that will equal 0. Okay, these are special trig limits. So let's see if we can do that with number 1. No, actually, we don't need to, right? This one is just fine to use direct substitution. Right, there's a 4 on the bottom, which is a number, so it's never going to be undefined. So let's just plug 0 into both of these things and see what we get. E to the 0 times the cosine at 0 divided by 4. Sorry, that's a 0, not a theta. Okay, so e to the 0, just like anything to the 0, is 1. The cosine at 0 is also 1. So 1 times 1 divided by 4 is? 1/4. So the limit of this function as x approaches 0 is 1/4. Okay, direct substitution here works just fine. And that's always our first try, is direct substitution. But notice here, right, it's not going to work so good. We have a 0 on the bottom. So this looks an awful lot like what we want, right? We want this to be sine of 4 theta over 4 theta, right? If we could somehow make this into that, then we would have our special trig limit. Okay, and we can do it, and we do it through multiplication.
Wait, okay. Why do you want to do sine?
Remember, to keep this thing mathematically legal, we can only multiply by 1. Right? Multiplying by 1 doesn't change our function at all. So if we want to have a 4 in the denominator, we also have to multiply by 4 in the numerator. Okay, so we multiply both sides by this fancy looking number 1. So that's the limit of, as theta approaches 0, 4 times the sine of 4 theta divided by 4 theta. Okay, now we're going to apply one of our properties of trig that says if we have a product, we can bring that out to the front. Okay, and the limit of a product is the product times the limit. Okay, so we're going to make that 4 come out to the front, and it's no longer going to be inside of our limit thing. Okay, this is one of the properties of limits that we can use and that you should use a lot in this case. So does this look like what we want it to look like?
Yeah, that's 1.
Yeah, that is 1. This whole entire thing is 1. The limit of this function is 1.
So you just drag out the 4.
I just drug out the 4 because that's one of those properties, right? Because 4 times the sine of 4 theta isn't the property. It's just sine of 4 theta over 4 theta. That's the property. So we'll pull that multiplier to the front of our limit rather than inside of our limit. And that's perfectly mathematically okay. So then 4 times 1 equals 4. So the limit of this function as theta approaches 0 is 4. Okay, the only way we can multiply and change is if we multiply by 1. So how about number 3 here? The limit as x approaches 0 of sine of 2 theta over 3x.
Oh, I know what we're going to do.
So we have to think of this thing as a product of 2 fractions. Okay, so follow me for a second here. What if I had the sine of 2x over just x? That means I would have to multiply this by 1/3. Is that the same thing mathematically? Right? It's 1/3. You do numerator times numerator, denominator times denominator. So I change my denominator into a product, right? A product of this thing that I want to try and manipulate a little bit times a constant, right? This is a constant fraction of 1/3, right? And since it's a product, it can come out to the front. One of those properties of limits is if you're multiplying by a constant, then you can pull the constant out to the front. Okay, I know, something that you really wouldn't think about as a normal person, right? Only crazy mathematicians think like that. Normal people don't. We're trying to help you become mathematicians. Maybe not crazy mathematicians, but at least mathematicians, right? So now it's closer to being what we want it to be. Okay, so what number do we want in the denominator in front of our x?
2.
We want a 2, so we have to multiply by 2 over 2. Right, we have to multiply by 2 over 2,
Oh, I see what you did there.
which is a 1, right? I'm multiplying by 1, which is perfectly mathematically legal. So then I also now take my product in the numerator, and I move it out front.
Wait, hold on. Okay, you're like, this equals 1.
Yep, so now we have something that is more like what we want when we're trying to use our special trig factor, our special trig limits. So we have 2/3 times the limit as x goes to 0 of sine of 2x over 2x. And all of this, right, this is our special trig limit. All of that stuff equals 1. And we're multiplying it by that constant of 2/3. So our final answer, the limit of that function, is 2/3. So we're trying to do some manipulation in order to make our special trig factorization look like it's supposed to, so that we can make it into a 1. Okay, that is the goal of these problems, is to do some mathematical manipulation to make our numbers into what we want them to be. Okay, so take a second, right? Pause the video, write this one down, work it out, and then come back and see if you got the answer. Okay, so here is how we do that mathematical manipulation. Taking our single fraction and changing it to a product of two fractions so that we can have a single theta on the bottom and you can multiply by whatever you want. Okay, so now our next one does involve some other operations with numbers, ones that we don't ever use either. Okay, in this case, we're going to split our sum, right? This is a single fraction. We're going to split it into the sum of two fractions. And we're going to apply one of the properties of limits. So we're going to take our sum and do this fraction, 4x over x, as one fraction. So we have the limit as theta goes to infinity of 4x over x plus sine of 2x over x. Yes, so if I were to ask you to simplify this, you would of course add these two fractions together because they have the same denominators. So in this case, I'm going to undo that, and I'm going to split this one fraction into the sum of two fractions. Okay, and I do that because it makes it very nice, right? X over x, that cancels out, so I'm going to have the limits of 4, basically, right, plus the limit of our second function. And this is one of those properties of limits. If we have the limit of a sum, that's not sim, that's sine. If we have the limit of a sum, we can change that into the sum of the limits and attack them each individually. Okay, that's really handy sometimes to be able to do that. Right, so the limit of 4 is just the number 4, right? A constant is a constant, so we don't have to worry about that one. Now this other one looks a lot like a trig thing that I want, right? If only the bottom were a 2. So of course I would multiply the top, which is just going to come out to the front anyway. So I am using some shorthand notation here and jumping a step ahead. Right? I would multiply it here, but then that just comes to the front. So I'm trying to save myself some space. And then all of this limit of this trig is 1. So 4 plus 2 equals 6. Okay, so that's a tricky trickster right there. We had one fraction that we split into two fractions. And we took the limit of each of those fractions separately. One became a constant, and the other became our special trig limit. Okay, so let's jump to our last one. We have 5 minus 5 cosine over theta. Okay, so what we want to do here is notice these both have a 5 as a common multiplier, so we're going to factor them out. Okay, because if we have a cosine as our trig function, we want it to be 1 minus cosine theta over theta. Okay, that's what we want because this special factorization is 0. Right? The special limit of 1 minus cosine over theta is 0. So if we pull out our 5, that makes it 1 minus cosine of theta all over theta, right? We factor out that 5.
But it's not being multiplied, it's being subtracted.
It's being multiplied by this whole entire 1 minus cosine thing, right? Because if I were to redistribute it, I would get 5 minus 5 cosine. So I first factor out that common 5 multiplier. And now I can use that property, which brings my multiplier to the front and no longer having it there. Okay, so that's something we're going to do a lot with these special trig factorizations, because then this whole entire thing is 0. 0. And unfortunately, we're still got to multiply it by 5, which turns out to be 0 anyway.
So, like, in these cases, the answer is always going to be 0?
I won't say always, but I believe most of the time, whenever we have a 1 minus cosine as our trig limit, the answer is going to be 0.
I mean, I thought it was hard until I did
Okay, so some mathematical manipulation so that we get to have a sine over sine or 1 minus cosine over theta.
Yes.